Okay. Big roll. Percy.
Here.
Morani just walked in. Gilcrease. Lucky, I think is online. Luna Sanchez.
Here.
Macias. McKinnon. Morris.
Here.
Powers. Renfro. Salvador. Spivey.
Here.
All right. So if I remember correctly, before I forget, somebody asked me a question concerning your test. If you look at this schedule in the syllabus, you're supposed to get your first test next week, but I've decided to put it off until the following week because we're still dealing with kinetics right now. I anticipate that we'll finish up on this today. Then you'll be able to do that assignment and turn it in, and then I'll grade it back and get it back to you so that you can have it to review. So I think you're going to need more time to review that, plus review the previous topic, which was basically colligative properties and solutions. So basically that test will be covering those two chapters, all right? So just to give you a heads up, you won't be getting the test next week, but the week following, all right? Okay, so with that out of the way, let me continue our discussion of kinetics. And if I recall, this would be the last topic that we discussed, the effect of temperature on the rates of reaction, right? And basically this is the relationship between the rate constant, K, and the temperature. There's some other terms involved. In fact, I think the next slide will give you the list of all those terms. Let me just, right, so basically, A is a frequency factor, and I think I told you what it is, but just in case I didn't, it's basically a term which represents the successful collisions frequency, and also the fact that the collisions are such that the molecules are oriented in the correct way so that the reaction will take place. EA is the activation energy, which I talked about earlier. It is the minimum energy that the reacting molecules are going to need in order for the reaction to take place. R is a molar gas constant, which I'm quite sure we're familiar with. And T is the temperature, absolute temperature in Kelvin. And I spoke about this, right? So this is the Arrhenius equation. Now, a more useful way of representing the same relationship is this equation here. This equation is just another way of representing or stating this equation. And just to tell you how we get from here to here, we find a natural log of both sides. So you have to go back to what you learned in algebra, right? If you find a natural log of K, you're going to get ln K here. And the natural log of that, let me see if I can write it. Up here. So ln K will be equal to ln, all of this here, A, e to the minus EA over RT. And this will be equal to ln A plus ln e to the minus EA over RT. All right. And then this would lead to ln A minus EA over RT, EA over RT. And this basically is the same thing as this right here, all right? Now, in this form, we can see that this is an equation of a straight line. If you notice that this would represent the y term, and the 1 over t would represent the x, right? So this is y, and this is x, right? So therefore, if you get, let's say carrying out an experiment where you measure or determine the rate constant at various temperatures, right? And then you find a natural log of the rate constants and you put 1 over the temperature, which must be in Kelvin, by the way, then basically you're going to get a straight line graph with a negative slope. And that slope is going to be equal to minus EA over R, and the intercept, so this is the slope right here. And the ln A here would be the intercept on the y-axis, so y-intercept, right? So basically, if you want to find the activation energy based on the graph, then basically you find the slope. Once you find the slope, then you multiply the activation energy by R. I'm sorry, you multiply the you multiply this, the slope by R, and that will give you negative deactivation energy, and therefore you can get the activation energy from that. As far as A is concerned, basically what you need to do is find where the equation cuts the y-axis, and that would be equal to ln A, and then from that you can find A. And I think I have an example right here where somebody did an experiment and plotted ln K versus 1 over T. I'm not sure what the reaction is, but in any case, the way you'd find the slope, of course, same as always, rise over run. In this case, it's going to be a negative rise over a positive run. So this person determined that the rise is minus 5.1. The run is 0.41 times 10 to the minus 3. And then that would be equal to the slope. In fact, let's do that calculation just for the fun of it. So the slope would be equal to minus 5.1 divided by 0.41 times 10 to the minus 3 Kelvin to the minus 1. So when we work this out, this gives you what? This gives you 5.1 divided by 0.41 times 10 to the minus 3. So according to my calculations, when rounded out to 2 sig figs, I got 1.2 times 10 to the minus 4, I'm sorry, 10 to the 4 Kelvin, all right? But remember now, that would be equal to the slope. So that would be equal to minus EA over R. R is 8.31 joules per mole Kelvin, all right? So therefore, to find EA, that would be equal to minus, oh, by the way, this should be minus here, right? Minus 1.2 times 10 to the 4 Kelvin divided by 8.31 joules per mole Kelvin. The minus signs will cancel out each other, so therefore I'm just going to divide the 1.2 times 10 to the 4 by 8.31. And according to my calculation, the activation energy for this reaction is 1.5 times 10 to the 3 joules, which would be the same thing as 1.5 kilojoules. All right, so that's basically how you can determine the activation energy and also the intercept. They didn't ask for that here, but if they did ask for that, well, you would be able to do it here because based on what I see here, where's this thing? Based on what I see here, the intercept would be somewhere above the minus 5 here. So they didn't extend the graph to that extent, so we cannot determine the intercept. But if you were asked to determine the intercept, then basically you'll identify where the line cuts the y-axis, and that would be ln A, right? And then you can find A from that, okay? And that's how you determine the collision, or I should say the frequency factor, right? So this is the most accurate way of determining the activation energy, right? By getting several data points of ln K versus 1 over T, and then you plot the graph, right? Now there's another way which is not as accurate, where you're only given 2 data points, right? And that way is in your assignment. So let me go there now. Oh, I didn't download it, so let me do that now. Assignments, assignment 2. And let's see what question I'm referring to here. Okay, here's it right here. Okay, so this question says calculate the activation energy for the decomposition of NO2. It gives you the equation and then it gives you 2 data points, right? It says that the temperature at 300 degrees, the K value will be 5.7 times 10 to the minus 1. And then at 230 degrees, the K value is 2.7 times 10 to the minus 2. So what we can say is that we can say that the 300 degrees is T1, but remember now, it has to be in Kelvin. So what you have to do is add 273 to that, and that gives you 573 Kelvin. And this will be T, not T, this will be K2, right? So this will be the rate constant when, I'm sorry, this will be K1. This will be the rate constant when the temperature is 573. And then for T2, we have to add 273 to that. So 273 plus 230, and that gives you 503. So T2 would be equal to 503 Kelvin, and the corresponding rate constant is K2, which is 2.7 times 10 to the minus 2. What the question is asking for is the activation energy, all right? So the equation that you would use is ln K is equal to minus EA over RT. Well, let me put 1 over T here, plus ln A, right? Now, basically, what we would have to do is write down different equations, or the same equation, I should say, but use different terms. So in the case of T1 and K1 relating to each other, let me do it here. ln K1 is equal to minus EA over RT. I keep doing that. Let me do it this way. 1 over T1 plus ln A. And then I'm going to write down here ln K2 is equal to minus EA over R, 1 over T2 plus ln A, right? And then what I would do is find the difference between this equation and this equation. When I do that, I'm going to end up with ln K1 minus ln K2, right? That would be equal to, as you all should know, ln K1 over K2, right? So that's what happens when you subtract this from this. You have to do the same thing with this from that, and that will end up being minus EA over R times 1 over T1 minus 1 over T2, all right? The LNAs will cancel out each other because when you subtract those two, LNA will subtract LNA, that will be 0, right? So this here is yet another way of expressing this particular Arrhenius equation, right? And this is useful if you have only 2 data points, right? It's not the most accurate because, as you all should know, the more data points you have, the more accurate will be the result, right? I would say that for something like this, you need at least 5 data points, okay? But if you have only 2 data points, then hopefully the 2 measurements are, pretty accurate in order for you to determine what the question is asking for, which is the activation energy, right? The question is asking for the activation energy. So we have to rearrange this equation here. So activation energy will therefore be equal to ln K1 over K2 divided by, and should be a minus sign here, and divided by 1 over T1 minus 1 over T2. So basically all we have to do now is put the numbers in. So let's see here. K1 is EA is equal to K1 minus ln K1. What's K1? K1 is 5.7. Yes, sir.
Where did the R go?
Hmm?
Would the R go anywhere?
Oh, the R should be there. It should be here. Thank you. So it should be minus R ln K1, K2 over K2 divided by 1 over P1 times minus T3. Okay, so, which means I need to correct here as well. So minus R, or let me put the value for R. R is 8.31 joules per mole Kelvin, right? Times ln K1, what's K1? K1 is 5.7 times 10 to the minus 1, m minus 1, s minus 1, divided by K2, which is 2.7 times 10 to the minus 2, m minus 1, s minus 1. And then I divide all of that by 1 over T1. What's T1? 573 Kelvin minus 1 over T2. What's T2? 503 Kelvin. 1 over 503 Kelvin. All right. And now we have to do the number crunching. So let's see here. What shall I do first? I'm going to do what's in the parentheses right here. So 5.7 times 10 to the minus 1 divided by 2.7 times 10 to the minus 2. And then I'm going to find the natural log of that. And then I'm going to multiply that by 8.31 negative. So the top part I got is 25.3. And the units for that would be, well, these units will cancel out. So it would be joules per mole Kelvin. And then for the bottom part, 573, 1 over that, minus 503, 1 over that, equals, now for this part, I got, there should be a minus sign here still. For this part here, I got minus 2.43 times 10 to the minus 4, and the units for that will be Kelvin. So let's see what that gives. So I'm going to divide 25.3 by 2.43 times 10 to the minus 4. And the answer I got, which I have to round out to 3 sig figs, is 1.04 times 10 to the 5. And the units here, the Kelvin units will cancel out because this should be minus 1, Kelvin to the minus 1. So the final answer would be expressed in joules per mole. And that's basically how that is done. All right. But I need to reiterate again that this would not be the most accurate way to determine the activation energy. The more data points you get, the better. And then you do the graph thing like I did the last time and get your slope. And then that will help you to get a more accurate value of the activation energy. This obviously would not be the most accurate because just in case the second measurement, for example, is wrong in terms of the rate constant or the temperature, then that would just basically mess up everything, and therefore your final answer would be less than accurate. Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Only one person out there in Zoom. Okay, so if there are no questions, let me give you some time to write it off. For those of you enrolled in my lab, which I think is all of you, not today's experiment, but I think the experiment next week is where you're going to be, at least part of it is where you're going to be plotting a graph to determine, I think the rate constant, if I remember correctly. I could be wrong. Anyway, okay, are we finished? Yes, ma'am. Yes, sir. Sorry.
How'd you find R again?
R is a constant, 8.31. Yeah, that's the molar gas constant, which will be provided for you, of course, in your test. Okay, any other questions? Any other questions? Okay, so let me clear this. Oh, it's still copying, sorry. All right. Okay, so let's clear this. Go back to the PowerPoint. And okay, so this is just rehashing what I said earlier about the equation. Well, this actually is specifically talking about the A part, which is called the frequency pattern. And I mentioned it very quickly, but let me take some time to mention this again. that the A part of the equation is the frequency factor, and it is the product of two things. One is the collision frequency, and the other one is a probability factor that takes into account the orientation of the molecules when they're reacting, all right? So that's the A part. Now this part here, the e to the minus EA over RT, represents a fraction of molecular collisions frequently energetic to produce a reaction. And I think in some textbooks, I'm not sure about yours, I think they use the letter F to basically be set as being equal to this, all right? F is basically the fraction of successful collisions that leads to product being formed. Okay, so next topic, reaction mechanisms. This is basically a fundamental concept we're going to look at, which applies not only to pure chemistry, but also in engineering, in medicine, and so on, right? Because what you'll find is that in order for us to understand the reaction, we have to understand what happens step by step, right? A chemical equation does not give us that information, because a chemical equation only gives us what you start off with and what you end up with. It doesn't tell you what happens in between. So whenever you hear the term reaction mechanism, we're referring to basically the detailed step-by-step process as the reactants are being converted to products, right? So as stated here, the overall progress of a reaction can be represented by a series of elementary steps, and that series of elementary steps would be known as the reaction mechanism, right? So just to give you a simple example, and some of these mechanisms are rather complex, but we're just going to focus on some simple examples just to illustrate this whole concept. So let's say we have this reaction, the reaction between nitrogen monoxide and oxygen to form nitrogen dioxide, right? So somebody was doing this reaction and they're interested in determining what the mechanism is, and they detected a different substance which is neither a reactant or product. And that substance is N2O2, dinitrogen dioxide, right? So basically, whatever mechanism that one can propose must take into account the formation of this substance which was detected, right? So basically, one can come up with a mechanism which accounts for this and accounts also for the overall reaction, which involves two nitrogen monoxide molecules reacting to form dinitrogen dioxide. So that explains the fact that this is detected. And then the next subsequent step is where the dinitrogen dioxide reacts with another molecule of oxygen to form two molecules of nitrogen dioxide, all right? So basically we have in this particular mechanism to explain this overall reaction, we have two, what we call elementary steps, right? And one thing about a reaction mechanism is that whenever you have two or more elementary steps, in order for that mechanism to be a valid one, when you add up these equations, you should get the net equation being the overall equation for the reaction, which is the case here, right? Because when you add this to this, if you recall from your general chemistry, whenever you're adding two equations, you have to make sure that items on either side must cancel out. Same is true here. The N2O2 and the N2O2 here, which is a product of the first step, is the reactant of the second step. Those two will cancel out each other. When you add everything else, you'll be left with the overall reaction, right? And this is true for every valid and legitimate mechanism. When you add up the elementary steps of the mechanism, the product or the result should be the overall equation, all right? So this is basically what we mean by the reaction mechanism and how it relates to the overall reaction, all right? Okay, any questions about this? Any questions? Any questions? Okay, so this is just basically the same reaction, but you're using models to represent the two-step process where two molecules of NO will react to form a molecule of dinitrogen dioxide, and then the dinitrogen dioxide reacts with a molecule of oxygen to form your final product, right? So that's basically what that is all about. Okay, now a couple of things that you need to learn, especially in terms of certain terms, with respect to mechanisms, right? There are certain species that are called intermediates, and these are basically substances or species that appear in the mechanism, but they do not appear in the overall balance equation. And the reason why is because in any mechanism, an intermediate is produced in one step, and then used up in a subsequent step, right? So overall, the intermediate will not appear in the overall equation, all right? So this is basically what an intermediate is in the mechanism. It's a substance which is produced in one step and then used up in a subsequent step, right? That's what an intermediate is. And we saw that in the example of the reaction that we looked at, the reaction between nitrogen monoxide and oxygen to form nitrogen dioxide. So as you can see here, the N2O2 was formed in this step, the first step, and then it is used up in the second step. And that's the reason why we can cancel them out in order to determine the overall equation, all right? So that's what an intermediate is. And that is different from a catalyst, which we're going to talk about shortly, right? Because the catalyst actually is kind of like the opposite. The catalyst is used up in a first step or initial step and then produced in a subsequent step. But we're going to talk about that later on. Some other terms that we need to be introduced to, this term molecularity, right? When we talk about the molecularity, usually, and this is a bit of a minor error, I would say. Let me make a correction here. The molecularity is not in reference to a reaction per se. It's in reference to an elementary step. So let me put that here. All right. So the molecularity of an elementary step is the number of molecules that are involved, number of reactive molecules that are involved in that step. All right, that's what the term molecularity is, all right, or what it means. And in this regard, there's some other terms, related terms. If a reaction is unimolecular, that means that the elementary step only involves one molecule. If the reaction is bimolecular, then that means that the elementary step involves two molecules. And then for the third one right here, which is highly unlikely, a thermomolecular reaction is where you have three molecules involved in the elementary step, right? If you think about it, use your imagination, molecules, bumping into each other and reacting, right? If you think about it, it is highly unlikely that three molecules are going to meet each other at the same time and then produce some products, all right? So the thermomolecular idea is largely theoretical, but very unlikely. It is more likely that you have one molecule reacting in a step. That would be the unimolecular reaction or unimolecular step. It is also very likely that two molecules will interact with each other and you end up with a product being formed. But for three molecules to do that simultaneously, very, very, very unlikely, all right? Okay, so now we can look at how the rate of reaction for each step relates to the concentration, right? And it's actually very simple, right? If you look at a unimolecular reaction, we can write down a rate law based on that fact alone, right? So the rate law for that unimolecular step is simply rate is equal to K times the concentration of A raised to the first power, right? If the reaction is bimolecular, let's say you have two different molecules, A and B reacting, then the rate of that step would be equal to K times concentration of A times concentration of B. Now, in a different type of bimolecular reaction where the two reactants are the same, A reacting with A, then the rate of that step would be equal to K times the concentration of A squared, all right? So these are basically the possibilities in terms of how you write down the rate laws simply based on the molecularity of an elementary step, all right? So just to summarize in terms of what we were discussing just now and previously, when you're writing a plausible reaction mechanism, the sum of the elementary steps must be such that when you add them together, you're going to get the balanced equation for the reaction. Now, this term here, I'm introducing for the first time. The rate determining step should predict the same rate law that is determined experimentally. Now, what do we mean by the rate determining step? The rate determining step is the slowest step in the sequence of steps leading to the product formation. So in a mechanism where you have more than one step, let's say 2 or 3, right? Then the slowest step is the one that determines the overall rate of the reaction, right? And we call that the rate determining step, Some textbooks, they use the term rate limiting steps, same thing, all right? So that is very important for us to basically determine or at least put forward a theory as to what the mechanism is for reaction, all right? So these are basically the sequence of steps that are involved in determining the reaction mechanism. First, you do some measuring of the rate of the reaction, and then you formulate the rate law, and then you put forward a reasonable reaction mechanism, taking into account the rate law, and also taking into account the balance equation for the reaction, all right? Okay, so based on what we have just covered, let's look at this example here. It says the experimental rate law for the reaction between NO2 and carbon monoxide to produce nitrogen monoxide and carbon dioxide is, and this is the rate law, rate is equal to K times the concentration of NO2 squared. The reaction is believed to occur via two steps, and it gives you the two steps here and here. So the first question is, what is the equation for the overall reaction? So what say you? Based on what we have just learned, what do you think is the overall equation?
Two plus CO.
NO2 plus CO to give,
And two. Here.
I'm sorry? NO plus,
CO2.
exactly, right. And how you determine that? Let me ask you.
You cancel out the NO2s on both sides.
You cancel out this NO2 with this NO2,
You cancel out the NO3s. on
cancel out
both
the
sides.
NO3 here and here, very good, right? So basically, those are the items that you will cancel out on either side, and therefore the overall equation is, as she said, what you see here, NO2 plus CO to give you NO plus CO2, all right? Any questions about this one? Any questions? Any questions? All right. Next question is, what is the intermediate? Now remember what I said, the intermediate is a substance which is produced in an initial step or a previous step and then used up in a subsequent step. NO3, exactly. NO3 is produced in the first step and used up in the second step. So the answer is NO3 for that question. Now the next question is saying, what can you say about the relative rates of step 1 and step 2? In other words, basically what this question is saying, which step is faster or alternatively, which step is slower? And the hint lies right here. So which of the two steps would be the, let's say, the slowest step or the slower step? Step 1, exactly. And why do you say that? Because the molecularity of this here is 2, which means that the rate of this step is equal to that, which is the kinetics, which is the result of the kinetic experiment that these guys have done. So therefore, the answer is that step number 1 is the slower step of the two, all right?
Could you explain that one again, please?
I'm sorry?
Could you explain that again?
Okay, so because the rate law says that a rate is equal to K times the concentration of NO2 squared, that tells you that the NO2 is involved in the rate determining step, right? And as you can see from this mechanism here, you have the two NO2 molecules involved in that step. So therefore, we know that basically this is the slowest step because that's what the rate law tells us. All right, okay, so now we're going to get into this other term, catalyst. I'm quite sure you would have met this term maybe in biology, because in biology, you'd have learned about enzymes, right? Enzymes are yet just one group of what we call catalysts. And in the case of enzymes, these are biomolecules which basically speeds up reaction rates. And that's what catalyst does. A catalyst will increase the reaction rate the rate of a reaction, but in the end, it remains unchanged, right? And the reason why catalysts work is because of the effect that they have on the activation energy. Remember, we talked about the activation energy, which is the minimum energy that the molecules will need in order for the reaction to take place, right? So the way catalyst lowers the activation energy, because that's what it does, is that basically it provides a different mechanistic pathway, right? So the mechanistic pathway for the catalyzed reaction would be different compared to the uncatalyzed reaction, right? And as a result, when you compare the activation energies of both catalyzed and uncatalyzed reaction, what you'll find is that in the case of the uncatalyzed reaction, the activation energy is higher compared to the catalyzed reaction. So basically, the reaction that is catalyzed will have a faster reaction rate. Why? Because if you lower the activation energy at the same temperature, all the conditions being the same, more molecules will be able to overcome that barrier, which is the activation energy, and as a result, the reaction rate will be faster, all right? So if you remember this equation here, if you look at the equation carefully, you'll see that the lower the activation energy, if EA is lower, that results in K increasing. And if K increases, that means that the reaction rate will increase because the rate is, of course, dependent on the magnitude of the rate constant, all right? So basically, as a result, the rate of the catalyzed reaction will be greater than the rate of the uncatalyzed reaction, all right? And that is true pretty much for all catalysts, be them enzymes or other biomolecules, or even industrial catalysts. We're going to see a few examples of catalysts at work and how they basically, how the mechanism changes when a catalyst is added. Okay, so there are two broad catalysts or two broad categories of catalysts, right? You have heterogeneous and you have homogeneous, right? So in the case of heterogeneous catalysts, the reactants and the catalysts are in different phases. A good example of this would be the Haber synthesis of ammonia. Another example of this would be the Ostwald process for the production of nitric acid, all right? Another good example of this, which you probably don't think of that much, are catalytic converters. These are basically installed in your motor vehicles nowadays so as to convert harmful gases like carbon monoxide and nitrogen monoxide and other gases that are products of the combustion of fuels into less harmful gases which you can emit into the atmosphere. Then we have homogeneous catalysts, and these are catalysts where both the reactants and the catalysts are in the same phase, and usually that phase would be liquid. And usually there are two types of homogeneous catalysts. You have acid catalysts and you have base catalysts, right? So that's as far as homogeneous catalysts are concerned. Now, going back to the heterogeneous catalysts, I mentioned the Haber synthesis of ammonia as a good example of this. So the Haber synthesis is a reaction, a very important reaction that was discovered by this guy by the name of Fritz Haber, who was a Jewish chemist. And he, this is the reaction right here to form ammonia, right? He's known as the father of chemical warfare. And the reason why is because he devoted a lot of his research into aiding the German effort back in World War I. So he decided, being a patriotic German, to basically use his chemistry skills to come up with chemical weapons and also some protective gear for the military that was serving Germany back then. Unfortunately for him, when Hitler came around, Hitler didn't care because he was a Jew and he had to find himself out of Germany very quickly, in spite of his patriotism to the country. But anyway, so basically what he did several things actually with regards to this reaction here. He looked at the effect of the pressure and the concentration of the gases, nitrogen and hydrogen, on the product yield, the product being ammonia, right? And he also looked at designing different catalysts for this reaction, because if you mix nitrogen and hydrogen together without anything, no reaction will take place, right? Because the activation energy barrier is too high. So he worked with different catalysts, and I think I have the combination that he came up with, right? So he came up with this combination, which is a catalyst that is used to make ammonia from nitrogen and hydrogen. Now, the way this works in terms of the mechanism is that the hydrogen and nitrogen molecules will be adsorbed, and this is the term, let me spell it for you, not absorbed, but adsorbed, all right? And what that term means basically is that the atoms are clinging to the surface of the catalyst, right? So what happens is that the catalysts have what are called active sites, right? So when the hydrogen molecules or the nitrogen molecules come into contact with that active site, an association or bond is formed between the atoms and the active sites. And at the same time, the bond between the hydrogen atoms and the nitrogen atoms are broken. So what you have basically on the surface are single atoms of hydrogen and nitrogen. And then they'll move along the surface and then come into contact with each other, where you have one nitrogen atom will come into contact with 3 hydrogen atoms. And then that is ammonia, and that is released from the surface of the catalyst. And that's how you end up with the ammonia. So that's basically how the mechanism of the Haber process works, all right? So that's a Haber process, which is an example of a heterogeneous catalysis. Okay, the other process here is the Ostwald process. And again, this guy, he was doing some research and he came up with this platinum catalyst, which will catalyze the combustion of ammonia to form NO. And then the NO will be oxidized to form NO2, and then the NO2 will be added to water to form 2 acids actually, nitrous and nitric acid, right? And basically that's how these acids are made industrially. And this is just showing you basically the catalyst, which is actually in this case, platinum and rhodium. What you'll find is that, you know, sometimes certain materials that are used in the lab would not be great for large scale production, right? So in the lab, it's okay for you to use platinum in order to carry out this reaction if you want to form small amounts in the lab. However, in the case of an industrial process, you might have to make some changes to the catalyst. So instead of just platinum in this case, platinum-rhodium combination is used for large scale production of nitrous and nitric acid, all right? So that's another example of a heterogeneous catalysis. A third example is what I mentioned before, catalytic converters, right? So as I said before, certain gases are produced as a result of combustion. And basically, one of them would be carbon monoxide, which is, as I'm quite sure you all are aware, is toxic. So basically, nowadays, motor vehicles are equipped with catalytic converters as a part of the exhaust system. And these are pretty expensive. I remember about 2-3 years, maybe 4 years ago, there was a rash of thefts. And I noticed it's mostly in California. I've never heard of it happening here, where people were actually cutting out the catalytic converters of motor vehicles, right? So you might be sleeping in your home and then wake up the next morning and go in your car and turn on the engine and hear this loud noise. And the reason why is because thieves have come and basically used saws and cut here and here and here to get the catalytic converters. And the reason why is because these converters are made up of very expensive metals, namely rhodium, palladium, and platinum. Those are the 3 metals that are used, and they are very expensive. I haven't heard of anything like that lately, but there was like, I remember, you know, I would see, you know, on my social media, like Facebook and so on, you know, videos of people going on the trucks and so on. There was one case where a lady fell asleep in her car and she heard a noise, and it was a guy trying to cut the converters, and she panicked, turned on the engine and drove off and ran over him. I don't remember, I don't think he died though. So that's another example of heterogeneous catalysis. Let me see here. Right, so for example, these gases, you don't want them in the environment. So basically, the converter will convert these gases into something more harmless, nitrogen and oxygen. In the case of carbon monoxide, that will convert to carbon dioxide, which is not as harmful as carbon monoxide, all right? And this here is a picture of basically where they cut off the external part of the protective material used for protecting the materials inside, which constitute the catalytic converter, just to show you what it looks like. Okay, I mentioned biological catalysts such as enzymes, and I'm quite sure, as I said before, you guys learned about this in your biology courses. So basically the way this works, there's this what they call lock and key theory for explaining how enzymes work. Basically, enzymes are huge biomolecules which have a specific shape that can adopt, or I should say, incorporate the substance, which is called a substrate, which will undergo the reaction. And basically, so this is a model of the enzyme. This is a substrate. As you can see here, the shape here will accommodate the substrate, so the substrate will fit into it. And then basically this would weaken whatever bonds that are present in the substrate. And as a result, the products will be formed and released by the enzyme, all right? So, for example, the enzyme that exists in our saliva, amylase, is used to basically break down any starch material that you might consume, and so on and so forth. And this is actually a three-dimensional space-filling model of such a reaction. Now, I don't remember what exactly the substrate is or what the enzyme is. But one of the things that you'll notice, and if you get into biochemistry, you're going to see a lot more of this. Basically, when the molecule fits into the cavity that is appropriately shaped so that it can accommodate, then there are changes that will take place in the rest of the molecule. And then, as I said before, there'll be some bond weakening taking place within the substrate, and then the product will be released. And the enzyme will be basically unchanged compared to before. So that's basically another example of catalysis, when it comes to biological systems. The kinetics of enzymes are kind of a bit different. This is showing you basically the energy diagram where you look at the substrate relative to the product for an uncatalyzed reaction, right? But when you add a catalyst, what you'll find is that there are two steps, right? There are two mechanisms, well, the mechanism involves two steps. The first steps involve this activation energy here, and then you get the enzyme substrate complex, and then another step which results in the product being formed, right? And then if you look at the rate of product formation versus the concentration of substrate, what you'll find is that when you increase the substrate concentration, the rate increases, which comes as no surprise. But you get to a point where when you increase the substrate concentration further, the reaction rate remains the same. And what that indicates is that all the active sites that were previously unoccupied by the substrate are fully occupied. In other words, it's saturated. So therefore, there will be no more active sites for any substrate to fit into. And therefore, it doesn't matter what the concentration of the substrate is after that point, you simply won't have the rate of the reaction increasing, right? So this is the equation which basically is used to indicate the rate of the rate determining step. Because if you look at this mechanism here, or this energy diagram here, the second activation energy is greater than the first, which means that this here is a rate determining step, which means that the rate is dependent on the concentration of the enzyme substrate complex. So rate is equal to K times the concentration of the enzyme substrate complex, all right? Okay, so that's basically it for this chapter. So going back to the assignment, we can now do question number 8. All right, so question number 8 is asking, consider the following elementary reactions. So you're given two separate elementary reactions. So the question is, first question is, in each case, what is the molecularity of each reaction? So here. Okay, so molecularity. What's the molecularity for this reaction here? Whoops. Well, remember what the molecularity is, right? Basically, the number of molecules involved as reactants in that step. So what would be the molecularity here? 2. What would be the molecularity here? Oh, by the way, Okay, this is not exactly a typo, but it might be difficult for you to realize that this is H, this is CL, and that's I, all right? I remember from previous semester, students were confused about that, right? So, okay, so HCl, right? That's a molecule. So what's the molecularity in this case? One, okay, very good, all right. So the next step, or the next question is, write the rate law expression for each. So let's do for one. What is rate equal to in that case? What is the rate law for the first reaction, or the first elementary reaction? K times concentration of
CO,
CO times
concentration of CO2.
CO2, exactly. And what about the second one? Rate is equal to K times
Yeah.
HCl, concentration of HCl. Oops, and that's it. That's all the question is asking for, all right? Okay, any questions about this one? Any questions? Okay. All right, let me clear this. Okay, so number 9, it gives you this mechanism, a 3-step mechanism, right? So the first question is, identify the intermediate and catalyst, if any. Now remember, let me remind you, an intermediate is a substance which is formed in a previous step and then used up in the next step or some subsequent step, right? The catalyst is used in a previous step, right? And then produced in a subsequent step, right? So please know the difference between intermediate and catalyst. An intermediate is produced in one step and then used up in a subsequent step, right? The catalyst is used up in one step and then reproduced or produced in a subsequent step. All right? Okay, so based on the mechanism that's provided here, identify intermediates, and it could be more than one, and catalysts could be more than one. And it says if any, in other words, there may be none. All right, so let's concentrate on intermediates. So are there any species that are produced in one step and then used up in a subsequent step? Hmm? Right, the Cl here, right? Cl is used up, is produced here, I'm sorry, and then used up here, right? So I would say Cl. Is there any other intermediates that you can identify? I'm sorry? The CLO, right? You don't have to put 2, just CLO. So the CLO is produced in that step and then used up in a subsequent step. So the Cl and CLO are the intermediates. So let's now focus on catalysts. Is there any substance which is used up in a previous step and then produced in a subsequent step?
CO2.
The Cl2, the chlorine molecule, right? I'm putting that in squares to distinguish between the two. Is there anything else that is used up in one step and then produced in a subsequent step? Or is that it? So I think that's it. So I'm just going to say Cl2 is the catalyst. All right, okay. B is asking, what is the molecularity of step number 3?
One.
One, exactly. All right, and then it says, which step determines the reaction rate and write the rate law for that step. Now, the key to answering that is those terms, right, beside each equation. So which step is the rate determining step? The first step. Okay, so step one, to answer the first part of the question. And what would be the rate law? Rate is equal to what? K times
Yield.
concentration of CO2. And that's pretty much it, all right? Okay, any questions about what we have done so far? Any questions? Any questions? Okay, so you finish writing? Okay, so, oh, yes, sir.
You do the part D as well too.
Yeah, I'm gonna do that, right. I just want to make sure you guys get this done before I scroll down. All right, so let me clear this. Let me do this. And let me scroll, oops. Okay, so it says, write the overall reaction equation and write the rate law. Oh, so there's a typo here. Ignore this part right here. Let me ignore this part. Where it says write the rate law for the overall reaction. So the only thing we're concerned with is the overall reaction equation. So let me scroll back up to the 3 steps. So basically, how would you determine the overall equation? What would you do? You cancel out those items that are common to both sides, right? So what would that mean in this case? What would you cancel out? The 2 CLs here and here. What else? 2 CLOs here and here. Anything else?
Yes.
I'm sorry? We did the 2 CLs already.
CO2.
Yep, CL2s. Anything else? No, so what would be left? 2 NO to give N2 plus O2. So that would be the overall equation. All right? So that answers the D part. Okay, any questions about this? Any questions? Any questions? All right, can I clear this? All right. Okay, let's see what's next. Okay, now this one has also another typo. Let me tell you where that is. There should be a K right here, so please make a note of it. A K should be right here. Rate is equal to K times the concentration of H2 times the concentration of NO squared, all right? Okay, so it gives you the balance equation, right? The question gives you the balance equation, and the question gives you the 3 steps, all right? And the question is asking that you show that this mechanism that is proposed is consistent with this experimentally determined rate law, right? So basically, these would be the 3 steps in the mechanism, and you are to show that the result of these 3 steps would be consistent with this rate law, all right? So what I'm going to do is scroll down because I'm going to need some space. All right, so the first thing I would do is, here it is here. Okay, so the first thing I would do is I would focus on the rate determining step, right? Now, based on the information provided in the 3-step process, the slowest step would be step number 2, right? So therefore, I would write down the rate law based on that because that would be the rate determining step. So based on that elementary step, rate would be equal to K2, that's a rate constant for that step, multiplied by the concentration of N2O2 times the concentration of H2, right? So that would be the first thing I would write down, okay? Now, the next thing I would recognize is that whereas H2 is one of the reactants in the reaction, N2O2 is an intermediate. Let me write that down. This is an intermediate, right? Now, the intermediate does not appear in the rate law, the overall rate law, right? So what I have to do is I have to find some way of expressing the concentration of N2O2 in terms of the concentration of the reactants, right? The two reactants would be hydrogen and NO, right? Now, how would I do that? Well, that would be based on the first step. The first step have two NO forming N2O2, right? And you'll notice that that's a reversible process, right? And let me just say that the next chapter we're going to deal with is basically going to be dealing with that kind of situation where we have two reactions going in opposite directions where the rates are equal. We say that, you know, that's a system in a state of dynamic equilibrium. So that's basically what we're dealing with here, but we're going to deal with that in more detail in the next chapter. Now, how do we deal with that? We assume for step one, that the rate of the forward reaction is equal to the rate of the reverse reaction. All right? So in other words, we're talking about an equilibrium type situation here, right? So if we assume that to be true, the rate of the forward reaction would be, based on what I see here, would be K1 times the concentration of NO squared, and that would be equal to K minus 1 times the concentration of N2O2. All right? This is for the forward reaction. This is for the reverse reaction, right? So we're assuming that the rate of the forward reaction for the first step is equal to the rate of the reverse reaction for that step, right? And then what I'm going to do now is rearrange this to get an expression for the concentration of the intermediate, N2O2, and that will be equal to K1 times the concentration of NO squared divided by K minus 1, right? So this would be, as I said before, the intermediate. And then what I would do is, where I have the intermediate here, concentration, I'm going to plug all of this where that is, right? And when I do that, where am I going to fit this? Let me put this down here. So when I do that, I'm going to end up with the rate is equal to K2 times all of this here, K1 times the concentration of NO squared divided by K minus 1, and then multiply that by concentration of H2, right? Now, if you look at this equation here to the equation that was shown earlier, let me scroll back up here. Remember now, there was a K here, right? If you compare this equation to this equation, you'll see that they're basically the same. The only difference is that this K here would be equal to this collection of constants right here, right? So therefore, if K is equal to K2 over K times K1 over K minus 1, then mechanism is consistent with the rate law. All right? And that answers that question, right? So because the rate law that we derive looks very much like this, with the only difference being that instead of just 1K, we have this collection of constant, we can say, well, that 1K is equal to that, and therefore the data, or the mechanism, I should say, is consistent with the rate law. All right? Any question about this? Any questions? Any questions? Okay, I'm going to leave the last, let me clear this here. I'm going to leave the last set of questions for you to do on your own. Basically, let's see here. These are just basically asking you to describe the difference between different terms that we covered. All right? And as I said before, this question here you don't have to do, but, oh, by the way, you were saying, telling me about, what was it? You were saying that there was something that you could not,
Can access one of those questions additional to that.
okay, let me see here. Oh, okay, it wasn't published. My fault. Okay, so now you'll be able to access those questions. All right, but I gave you a handout with it already, right? Right, so, okay.
I was in Zoom that day.
Oh, okay, right. Okay, right, so make sure you do those questions and attach them. In fact, let me now set up a Dropbox for this assignment. So this is assignment 2. And, okay, so. Okay, so I'm going to make this, the deadline be Friday. Let me, okay, so available from today, which is today. And then this will be Friday the 31st. Okay, so everything looks good. Okay, so make sure you submit it by that date, midnight, deadline. And that's pretty much it for today, unless there are any questions you guys have. Okay, so that's pretty much it. I'll see you guys. So, in the lab. Yes, ma'am. Okay, so between 30 and 40.
True and false, I kind of.
I was like- She said just to like those questions. I did, and some of them didn't have the answers, so.
2 times 10 to the minus 3, right off was it big, and then. Then 73 minus 0.11 divided by 30.
I like it.
That will be 1 times 10 to the minus.
So it's like the square root of.
Oh, no, wait a minute.
Minus 1 plus.
Plus two, okay,
Yeah.
that's right.
Oh, what did I say?
As long as that's not like kids with us.
Yeah, it's.
Like the whole is like.
Okay, wrong number here.
Question.
You should have used
I mean-
0.054
It's
here,
like,
because that's the number that corresponds to the 40.
I don't know, I put like question.
You see what I'm saying?
Yes.
So you should have 0.073 minus 0.054, and then divide that by 30. Ooh, oh, yeah, right?
Yeah, because it's a jump.
No, what am I saying? Hold on. It should be 0.054 minus,
Yes.
0.110.
No, like it's.
Oh, okay.
It's supposed to be.
0.054 minus
Okay. I'm not ready for the
0.110
test, though, I was like.
divided
yeah.
by 30. That would be 2 times 10 to the minus 3. Again, round off to 160. Right.
This minus this.
Yes, exactly. So,
It's like,
right.
you know what, looking at this, there's no.
So just replace the 0.073 with 0.054 minus that.
It's just two.
And the answer will still be 2, yeah.
Thank you.
Yes, sir.
Is that a question of, under P, or like?
So.
No, what the question, we did an example of this, we use a pencil. We did an example of this, previously.
Those, I think it are.
I'm hoping so, but there's like some.
So basically, you're gonna compare, okay, this one is actually easier than the one that we did, because basically, you're gonna compare, these two experimental data, right? So I'll write down a general rate, here. Rate
But.
is equal
I'll
to
see
K
a lot.
times the concentration of ArSO2 is, right? And then, for experiment 1, the rate would be 4.75 times 10 to the minus 5 over S equals to K times 0.25. Oh, by the way, this should be raised to the power, which should be combined.
Yeah.
All right, and X, and then for experiment 2, 6.84 times 10 to the minus 5 M over S equals to K times 0.30 M raised to the X. And then you divide the top line by the bottom line. These will cancel out. So you're going to be left with 4.75 divided by 6.84 equals to 0.25 divided by 0.30 raised to the M. And then what you'd have to do next is do the division. So this part here works out to be 0.694, and then 0.25 divided by 0.3 equals to 0.83 raised to the M. So the question is, what is M? And by inspection, I can see that M, oh, let me see something. Right. M will be equal to 2. Because 0.83 squared, which is what I just did, would be equal to 0.694, right? So M would be equal to, so that's basically how you do it. Right. And the other 2 questions additional question that he was asking about, same process, but it would be a bit more challenging because there are more than one reactor.
Wait, you said this would be 2 because that square is.
Right, because 0.83 squared is equal to, there's a longer way of proving it, but,
Because I know I did, I did 12 before you said. no.
oh, right, yeah, 12 is kind of,
And I used, because.
use logs.
Yeah, logs, or well, natural logs.
Well, you could use natural logs or just log to the base 10.
Because I was like, this doesn't make sense for me to use logs.
Right,
This is-
yeah, but, okay, let me show you, because like in this case here,
I didn't round up for the other example, but I'm pretty sure.
let me show you, in this case here. Let's see, okay, so in this case here, instead of doing what I just did because I just inspected it,
Yeah.
you do log of both sides, right? And then this would be equal to M log of 0.83. Therefore, M would be equal to log of 0.694 divided by log of 0.83, and you're gonna get the same answer. So 0.694 log of that divided by 0.83 log of that, and you're gonna get 1.96, which is about 2.
All right, thank you so much.
Yeah, no problem.
I had a quick question.
Yes, sir.
A question about more, so that's for the contract. So this is that's the 0.
Right, exactly right.
So then you just plug this in for the T value, right?
Right, and the initial concentration is given,
Right.
right? And I think K is what you got K here,
Okay.
right? And that goes here. And you just plug the numbers in.
Okay. But this is the react like that.
That's the reactant concentration at time T,
Okay.
all right?
Got it. Thank you. And you said it's, the test is exactly a week afterwards, so. it's
Yeah,
Thursday
right,
after
because
that.
I want to grade like the kinetics one and get it back to you guys so that you guys can review it.
All right, thank you.
Yeah,
I'm good, very well, I'll see you in like 30 minutes.
yeah.
Definition, because I'll walk on some of them. I know I can find these two, but I was thinking.
Well, okay, so adsorption is what I described before, is where substance cling to the surface of a solid, right? Absorption is something like a sponge absorbing, let's say, water, where the substance is not just on the surface, but it's absorbed, it permeates the substance, so that it goes beyond the surface. So that's the difference between those two.
And when I'm writing them down, could I look them up?
Yeah, sure, no problem. And then, average rate and instantaneous rate, we covered that earlier. The average rate is the rate measured over a time interval,
Mhm.
while the instantaneous rate is the rate measured at a particular time.
Okay.
Right, so that's the difference between those two.
Okay.
Yeah. Okay, let me shut this off.
And I did finish all my pre-lab questions.